Okay. Does the mean value theorem satisfy the hypothesis? Does the following satisfy the hypothesis of the mean value theorem on the given interval? Why or why not? For those that satisfy the hypotheses, find the values C that satisfy the conclusion of the mean value theorem. Now, if this shows up on a test or quiz, if we have quizzes, who knows? I'm recording these lectures during the pandemic, so I don't know exactly what things will look like while you're listening to these lectures. But let's say we have tests or quizzes. I'm not looking for major mathematical proofs as far as the hypotheses. We've got f of x equals x to the 2/3. Make that so it's legible. And it is good enough for me just for you just to write that that is continuous on -1 to 2. Primarily in this class, not because of all mathematics, no division by 0. Now, that's not true for all of mathematics. Remember, continuity actually has 3 conditions that at each point that you're talking about, that you want the function to be defined, you want there to be a limit, and you want the function and the function and the limit value to be equal to each other. That's continuity. But for the vast majority of things that we're going to deal with, as long as you avoid division by 0, you're going to be continuous. Again, just what we deal with in Calculus 1 in this class, not continuity for everything. Continuity was a point-wise definition. So if you're talking about continuity at C, it was f of C is defined, the limit as x goes to C of f of x exists, and that f of C equals that limit. But for our work, avoid division by 0 will be good enough. 2 talks about the derivative. Well, let's take that derivative, and that is not differentiable at x equals 0, so, which is in. Let me simplify a little bit. I think probably left some people. I just said it's not differentiable at 0. Let's rewrite this thusly. And then we can see that it's not differentiable at 0, which is in the interval in question, -1 to 2. So the hypotheses are not satisfied. And so I stop. It says for those that satisfy the conditions, doesn't satisfy the condition. At x equals 0, my derivative is undefined. That if I try to put 0 into my derivative, I'm going to have division by 0, and the world just doesn't work well for division by 0. The world doesn't work at all when division by 0. So my hypotheses are not satisfied, so this problem is done. No point in searching for that number C that satisfies the conclusion. The hypotheses aren't satisfied. So moving on. And notice we've got the same function now, but a different interval. And the interval is going to make all the difference in the world. But going through the same thing, f of x equals x to the 2/3. It's continuous on, in this case, 0 to 8. Again, there's no division by 0. And let me again emphasize there's more to continuity than that. Continuity, we talk about point by point. If you're talking about at C, you want f of C to be defined. You want the limit as x approaches C of f of x to exist, and you want the limit as x approaches C of f of x to equal f of C. Continuity really has 3 things going for it. But for our work in this section, and for most of our work in Calculus 1, avoid division by 0. Then the same thing with the derivative. We still have division by 0, at x equals 0, but that is not in the open interval 0 to 8. Remember, parentheses exclude the number. So we got 0, but 0 isn't the open interval. And the hypotheses, there's the word I want, the hypotheses for differentiability was on the open interval. So we should be able to find that value C. So we want to find the value of C that satisfies f prime of C equals f of B minus f of A over B minus A. So what we're going to do first is we are just going to set this equation up for the interval 0 to 8, which gives me my A value and my B value. So we are just going to set it up where we have f of x equals x to the 2/3. So f of A is going to be f of 0, 0 to the 2/3, 0. F of B is going to be f of 8, 8 to the 2/3. And remember, that means the cube root squared, so 2 squared and 4. So then I can say f of B minus f of A over B minus A is going to be 4 minus 0 over 8 minus 0, or 1/2. So there's f of B minus f of A. Recall f prime of x was 2 over 3x to the 1/3. So just being really, really specific, since they said find f of C, I'm just going to put a C in there. If you work the problem with an x there, no one's going to care. But since they told me to find a C, I'm going to make my variable C. But if you used x, yeah, it just doesn't matter. So that tells me that this equation I want, that I'm setting up, f prime of C equal f of B minus f of A all over B minus A, becomes 2 over 3c to the 1/3 equals 1/2. There was the f of B minus f of A. Make sure you can see it. There we calculated what f of B minus f of A was, all over B minus A. That was 1/2. There's f prime of C. The equation says set those guys equal to each other and solve. So solve this. It's proportion, 2 equal fractions. So my best bet right off the bat is to cross multiply, which will give me 3c to the 1/3 equals 4. Divide both sides by 3, so c to the 1/3 equals 4/3. Then cube both sides. And so I get C equals 64/27, and that's the answer you should give me. But just for purposes of understanding better what that value is, 64 divided by 27 is roughly 2.37. We said that there should be a number C between A and B, 0 and 8. We got it between 0 and 8. Now let's look at a picture of this. So I'm going to graph the original function, which was x to the 2/3. Yeah, you can sort of see it right there. So clear that. X to the 2/3. Older calculator, be sure you put that exponent in parentheses. And then it said we were on the interval from 0 to 8. I'm going to just go a little bit further. I'm going to go from, clear that. Oops, didn't mean to do that. Let's try this again. X to the 2/3. And I'm going to press my window. They said 0 to 8, so I'm just going to go a little bit further. -1 to 9, just going a little bit further. And I really don't have much information on the x's, on the y's, so I'm just going to kind of guess on the y's, and I'm going to go from -5 to 5. That's just a guess as far as the 5s are considered. And I'm going to graph it now. Okay, so there's my graph. Let's try to get a little bit better picture. I certainly didn't need the negative values of y, and maybe I needed to go a little bit higher on the positive values of y. So let's go, instead of -5, let's go -1, and maybe go to 7. Again, just sort of guessing and graphing that. Now I should have picked a better example here, because that guy's almost straight. But if we go to x equal, we got 2.37. So let's do a trace, and x equal 2.37. Go there. I really should have done a better example that's curvier. But you might sort of be able to see it. The tangent line, or the secant line between those two guys would be roughly there. That's where the secant line would be. And then we're saying that the tangent line at that point would be parallel. And it looks like it probably is. I really should have picked a better example where this is curvier. I mean, that's almost straight, so it's hard to see the tangent lines when it's almost straight. But remember the secant line, and let me graph this one more time and really graph just to 8. They said 0 to 8, so I'm going to graph 0 to 8, graph that. So the graph's coming up again. And we'll do a trace. And I'll just put in my estimate. Well, actually, I can put in my real value. 64 divided by 27. It'll be okay with that. Enter. And so the white line would be the secant line between the endpoints. Then what the mean value theorem is saying is I should find a point where the tangent line is parallel. So if you envision drawing a tangent line right there, it does indeed look like the tangent line will probably be parallel. And if we try to get a picture, one more better picture, when I went up to 7, and it looks like maybe I could have really stopped at 5. 1, 2, 3, 4. Yeah, I think I could have stopped at 5. So let's go to the window one more time. So going to 7, let's go to 5 and see what we get. We might even get a better picture. And this is the problem with just kind of guessing around without finding actual values. Okay, that looks pretty good. And then trace 64 divided by 27. There's that point. So the secant line would be right about there. There's the secant line between through the endpoints. And then envision, if I drew a tangent line at that blinking cursor, it does look like it would be parallel. And so these guys check by looking at a picture. That what the mean value theorem is saying is that you can find a place where the tangent line will be parallel to the secant line. And it really does look that if I drew a tangent line at that blinking cursor, it would be parallel to my secant line, which is the white edge there. Okay, that's all we're doing with the mean value theorem. So that's the end of this lecture, or end of this video, and end of the lecture on section 4.2, mean value theorem.